Welcome to Lecture 15 on the topic of precision agriculture. This lecture is part of the subject Future Farming Technologies. This subject is a component of the Bachelor of Agriculture and Technology, a degree offered at both North Melbourne Institute of TAFE and Melbourne Polytechnic. Please visit our website www.nmit.edu.au for further information on this course and other courses that we offer. My name is Dr. Nikki Cooley. In Lecture 15 we will introduce precision agriculture to you. This is often referred to as PA. We will look at the commercial objectives of PA and some of the assumptions underpinning PA. We will complete the lecture with a suite of case studies and research across a number of areas of precision agriculture. In this lecture we will be covering the following three student learning objectives. You will learn how to use and explain the interrelationships between technology, performance, sustainability and production efficiency in agricultural industries. This is part of student learning objective number 2, where you examine and evaluate different technologies. This is an extension or application of the GPS and GIS information covered under this learning objective. And finally, you will learn how to interpret, communicate and present ideas using appropriate terminology for this topic. Most crops will show some kind of variability in the field environment. This may be evidenced or seen as variation in crop yield or leaf area, photosynthetic capacity, germination, flowering, or really any part of the physiological process and growing process. So it's not an unreasonable question to ask, does this variability matter? Does it impact on production? How much does it cost your enterprise? If you cannot record the variability, then you have no way of knowing what it is, and therefore you do not understand if it's a problem. The purpose of precision agriculture, put simply, is a management tool that enables the farmer to deal with the variability in their enterprise. The term precision agriculture, or PA, originates from a workshop held in Montana State University in 1990. Before this date, it was referred to as site-specific crop management. A more technical definition is presented on the slide. PA can be thought of as an integrated information and production-based farming system that is designed to increase long-term, site-specific and whole farm production efficiency, productivity and profitability while minimising unintended impacts on wildlife and the environment. Precision agriculture can be applied to a number of different enterprises. Some examples include agronomical crops, the hydroponic industries, the dairy industries, environmental practices and its monitoring, and economics. It determines within crop variation using a range of tools if we look at the agronomical examples. From an agronomical perspective, you would monitor both the crop inputs, that is, of a direct nature, such as nutrient and water, and an indirect nature, perhaps the soil. And you would also monitor the desired outputs, for example, yield. There are a suite of commercial outputs that are theoretically possible from precision agriculture. These include, but are not inclusive to, within-season information to the farmer, across-season or season-to-season information to the farmer, a technique that can enable accurate record-keeping and determination of historical significance specific to your enterprise in your location. It will assist in management and aid decision-making. This will ultimately lead to improved input resource efficiencies, improved inherent farm qualities, and possible climate change adaptation strategies. Other commercial outputs include that in some industries it claims to and can improve quality. Importantly, it enables system optimization, or at least the potential for system optimization. And what we mean by this is it optimizes your enterprise in your climate or environment or location, or your market conditions with your resource input capabilities. And all of this, and perhaps the most important claim for this type of technology, is that it will make you more money. Precision agriculture is traditionally conducted across 4 stages. Firstly, geolocation of your data. Secondly, characterizing your variability. Thirdly, making some decisions based on your variability characterization. And fourthly, implementation of your decisions. So, some of the technology that enables geolocation of data we have already covered in previous lectures. There is GPS, this is where is the farm, where are the areas of monitoring to be conducted. There is GIS, which is where you take the information and you overlay it to enable a visual representation of your data. Some of the examples of information that you may collect are your soil type, your depth, your pH, your EC, your soil composition, or the nutrient status of your soils. GPS references of paddocks and buildings are also important in the visualization characteristics. Information may be collected on ground or via satellite imagery. Layered information across hierarchies needs also to be considered, particularly interpretations. The next stage is for characterizing variability. Field variability may result from a number of inputs, such as your climatic conditions, rainfall, wind, your soil types, as we discussed in the previous slide, cropping practices, for example, if you're in agronomy you may have tillage, and or weed and disease susceptibility. The next stage is to make some decisions, and we call this the decision making. The farmer would get the information they require from the spatial maps they have created. This would include information on the various inputs and some of the outputs of their enterprise. The farmer can select one of 2 possible methods for making a decision. The first he may choose to select is the predictive approach, where the decision is based on the analysis of static data, such as that of nitrogen soil concentration. A predictive element is required in this type of approach. The second method is called the control approach, and this is perhaps the most commonly used approach. Data is regularly updated to give temporal information. As the information is updated, management decisions can be adjusted if necessary. This is what we call a real-time approach to decision making. Decisions as support models can be used for this kind of approach, and these are often referred to as crop stimulation models. Manual sampling, automated sample collection, remote sensing and or aerial satellite data can be used with this method. The next stage is implementation. The aim of this is to address the variability by implementation of a management decision. Usually you require variable rate technology to support the implementation if you're dealing with zoned variation. This can include GPS, DGPS and GIS technologies. Location and layered data, depending on the source and the application, requires visualization of the variability. Precision agriculture is an evolving beast, and there are some common current commercial trends currently. One of them is to significantly improve the accuracy of GPS. Ideally, you would take it from meters down to centimeters. Technologies involved in this are real-time kind mathematics, or RTK corrections. This sort of application and technology is required for such techniques as strip tillage, fertilization and planting. Other commercial trends are to explore input management, that is, to make your fertilization and pesticide applications more precise. This requires the technology of variable rate seeding and variable rate applications. Finally, solutions for information management. How do you actually make the decision? One of the problems of this technology is you get so much data. What does it mean? How do you make a zone? Where do you draw the line? There is now a suite of technologies available, and more to be developed, I suspect, that will enable decision making, utilisation of yield data and zone creation. Tracking systems are a very important component of the technology required in precision agriculture. There are two types to look out for: light bar or parallel tracking. This is where the farmer still drives the machine. Light bar will provide GPS data feedback, i.e. where are you in the paddock. Auto guidance is another tracking system. This is where the machine on the whole drives and navigates itself. The operator is still required, though, to turn the machine and line it up to the next pass. In order to enable precision agriculture, there are a number of technologies that a commercial system may contain. On the next couple of slides, I have outlined a typical or an example of a commercial system. You may have a system that has real-time biometrics in, or RTK. This requires a base station and allows for your accurate GPS correlations to be made. You may have spray tractor installed with nozzle control technology. This enables the variable rate application of your herbicide, fertilizer and/or pesticide. Variable rate technology is where you change the rate of application depending on the variation. This application requires sensor feedback or some kind of signal information to inform it about where to make the decision. I have listed all the examples on the screen of how variable rate technology is currently used. And finally, there may be wireless sensors scattered around your farm collecting information, perhaps on your soils or your climate or some other aspect of your enterprise. This information would need to return to a central controller where further decisions can be made. Site-specific crop management is a strategy developed to match your variations in your system, i.e. your inputs such as your soil, that are known to cause the variation and can be controlled to your crop requirements. This is largely used in agronomy and it's referred to as yield mapping. So let us examine some of the steps that you would undertake in order to do some precision agriculture. We will start with an example of soil as a factor. The first thing you would do is take measurements of your soil and obtain a visualization of these measurements. I have decided to use soil pH as an example, as this is something that you are all capable of doing and could in fact practice. Once you have got your visualization and your soil pH measurements, you then need to define boundaries. That is, you need to define your field, your paddock and/or your testing strip, depending on why you want the information. Your next stage is to label the variation of your soil. For example, label that you are collecting soil pH. You then need to set boundary ranges. In this example, I've identified pH units of every 0.5. Boundary ranges and how you make these decisions can be complicated. Sometimes you can use your extensive knowledge of understanding the link between a plant nutrient uptake, say, and soil pH, as I have done in this example. Or there may be other components, such as how the measurement is collected, which will define your boundary ranges. Once you have defined your boundary layers, I've given some examples of soil pH ranging from 4 to 6.5, you would want to assign each boundary a range in colour. Usually the colour has some kind of relationship. In this case, the more acidic, the lighter the colour. Once you see your variation, the next stage is you have to define major zones across your area. You can do this by a number of methods. You can look and see where most of the pH ranges are clustering, or you can apply some sophisticated statistics to enable boundaries to your ranges. Then, once you have assigned major zones, you would then adjust your pH. This you will need to do off-season, as this kind of management technique requires the paddock to be bare. You would probably implement variable rate technology to apply lime to assist with the adjusting of your pH. Of course, how you adjust your pH will depend on your soil structure and the economics. There may be areas of your soil or enterprise that just aren't worth the economics that it requires to adjust pH. Also, it should be noted that several applications of lime are usually required to make large pH changes. Therefore, this strategy may take several years to complete. The first case study I'm going to start with is precision agriculture for agronomists. I'm going to introduce a commercial precision agricultural product. This is an example of a Trimble Nomad GPS unit with a crop biomass stability map that was made with the aid of the GPS unit and crop biomass data. This is a commercial service where data acquisition, processing, provision in suitable format and integration of the associated crop monitoring, soil and plant testing and determination of input rates are all offered. Other services that you can access via this site is satellite imagery data and yield mapping. This gives a snapshot of one such commercial product. Please note, I am not recommending this product over others, rather including it as one example. The company Precision Agriculture also offer other services such as training. There are 3 courses that you can attend for a fee: Training Farm Ready Workshop, Online Farm Ready Workshop and Training for Advisors and Agronomists. Other services included are loss assessment, loss assessing, insurance and liability industries, which may also use this technology. This will enable loss assessment using remote monitoring tools such as satellite imagery and yield mapping, preparation of professional reports for loss assessors, insurance and legal requirements, and expert witnesses in court proceedings if they should be needed. In this paper, The Adoption of Precision Agriculture in Australian Broadacre Cropping Systems, the challenges and opportunities were reviewed. The purpose of this was to increase industry adoption of this technology. It had noted that there had been an investment of machinery guidance systems and yield monitoring in agronomy, and on the slide is an example of such an output. This paper went on to further look at the adoption of spatial variability technologies across farming zones, a part of precision agriculture. They found that there was an inhibition to this part of the technology. They found that this inhibition was due to cost, difficulties in integrating components, problems with data interpretation, and issues of using the spatial information to enable agronomic solutions. One of the reasons for this inhibition of adoption was shown to be that there was little demonstration of the technology capabilities in spatial variability. In this research, the grower group Wimmera Conservation Farming Association undertook the challenge to look at implementation and uptake of PA. They did this by forming focus farms. This was to demonstrate the spatial variability assessment, applications and outcomes of PA. They looked specifically at methods to measure efficiency gains against the capital outlay of different PA systems. They concluded that on average PA costs the farmer between about $20 per hectare per year, which can be spread across 5 to 10 years, where you are cropping an area of about 1,000 hectares. These figures will of course change depending on how you measure your temporal and your spatial distributions. Further adoption enhanced by reduced implementation costs, and this is in fact a trend of this technology. The following article by Robertson et al. In 2007 is a joint CSIRO and GRDC report. It can be found on the following URL link for your information. This report is titled The Economic Benefits of Precision Agriculture, a case study for Australian grain farmers. This report aims to identify why there has been a low adoption in agronomy. It concluded that it was probably due to expensive setup costs. It has looked in detail at the setup costs of 6 farms in this case study. The case study covered a range of agroclimatic regions, Mediterranean type, uniform, summer and dominant rain patterns. It looked at a number of cropping systems including wheat lupin, wheat canola, winter and summer crops. It looked at a range of farm sizes and soil types. It also looked across a range of production levels. For example, in the wheat case studies, production output ranged from 1.8 to 3.5 tonnes per hectare. You will note that this is quite a low production rate. The farmers had been involved in the study for 2 to 10 years and covered the range of PA technologies that are commonly used among Australian grain farmers. Among the 6 farmers, all had invested in guidance and were practicing some of the variable rate management of fertilisers. However, only some were using auto steer and tram lining. One was using NDVI and another the Green Seeker technology for in-season nitrogen management. As such, the data set covered the range of likely situations confronting practitioners of PA in the Australian wheat belt. The report concluded a number of important outcomes about the economics of PA in agronomy. The level of capital investment in PA varied from 55 to 189,000. Capital investment per hectare crop varied by a factor of 3, from $14 to $44 per hectare. The estimated annual benefits from PA range from $14 per hectare to $30 per hectare. And I guess the take-home message is that investment analysis showed that within the 6 case studies, the initial capital outlay was recovered within a range of between 2 and 5 years. All farmers were able to quantify benefits of variable rate fertiliser management, and this ranged from $1 to $22 per hectare across the 6 farms studied. On a per paddock basis, benefits ranged from $28 to negative $28, to $57 per hectare per year, quite a range. Variation in monetary benefits from farm to farm could be explained by either whether or not fertiliser was applied initially, and if it was it just nitrogen top dressing, and 2, the degree of within paddock yield variation. The methodology for estimating the benefits of variable rate technology requires further testing on a paddock scale data where yields and fertiliser rates are recorded for uniform VRT managed strips. In a paper by Gasserman in 1999, the ecological intensification of cereal production systems was evaluated. Yield potential, soil quality and precision agriculture were all discussed. This introduces us nicely to PA and sustainability. It was noted by Gasserman that the gap between average farm yields and the yield potential ceiling must shrink during the next 30 years because the yield potential of tropical rice and maize appears to be stagnatant, and wheat yield potential is increasing more slowly than expected increase in demand. This has been seen in other areas of farming, such as the dairy industry too. It has been cited that the reason the increases are not as prevalent as they once were because of intensive farming system technologies. It has been noted in this paper the negative environmental impacts that intensive farming systems have resulted. PA is cited as being a tool to manage and therefore reduce the negative environmental impacts. PA can help to ensure that the requisite resources for crop growth are available and crop production needs are met without deficiency or excess at each point in time during the growing season. It is important to note that PA can account for variation in soil properties, variation in crop resource requirements, and variation and responses to both pest and diseases. Thus, PA can assist with the knowledge gaps to enable further optimization, and this is seen to have significant advantages for the environment. Now we'll look at what are called crop biometric maps, which can be a technology of precision agriculture. Francisco, 2013, published a paper, an overview on crop biometric maps. It was stated in this paper that crop biometric maps were the key to prediction. The aim of the research was to enable an investigation into how do you cope with the vast variability of nature and the uncertainties of agricultural production. The definition of crop biometrics is the scientific analysis of agricultural observations confined to spaces of reduced dimensions and known position with the purpose of building prediction models. In this study, wine production vineyards and canopy cover and quality attributes were explored. It was concluded that prediction models for yield and quality were developed for high and low resolution maps, and these showed the greatest potential for crop biometric maps as a strategic tool for vineyard growers, as well as for crop managers in general, due to the wide versatility of the methodology proposed therein. Therefore, it can be concluded that crop biometric maps are a good strategic tool for vineyard growers, and they can also be used for other crop managers. Therefore, because of the wide versatility of this technology, it is a good methodology. Precision dairy is where precision agriculture fundamentals are applied to the dairy industry. Jago et al. 2013 published a paper entitled Precision Dairy Farming in Australasia: Adoption, Risks and Opportunities. It is stated in this publication that precision dairy enables larger herds and increased complexity in farming systems, and it combines this with the availability of new information technologies, and this is why precision dairy is being taken up. PD is being conducted via automatic and the collection of fine-scale data on animals and farm resources. It states in this paper that the uptake of PD at this moment in time is on the low side, with only between 10 and 20% of farmers using this technology. It also states that there are a range of attitudes towards the uptake of precision dairy technologies. Some farmers have positive attitudes and stories, while others have negative perceptions of these technologies. In this case study and research, a number of focus groups were set up, and the aim of these focus groups was to enable the adoption of PD and overcome some of the issues that some of the farmers may be encountering. For those that successfully took up PD, this publication states that there was improved management possibilities. Berger and Habav in 2014 published a paper entitled Using a Dairy Management Information System to Facilitate Precision Agriculture, the Case of Afi Milk System. The aim of precision dairy, as stated by this paper, enables product quality, reduced labour costs and balanced product mix in a dairy enterprise. In this study, dairy management information systems were implemented by SEAE at AFRICAM to illustrate the applicability of systems in precision ag. This study outcomes were that 6 Sigma-based dairy management information systems can support 4 or 5 propositions. These include reduced product defect, optimal product mix, increased equality, and better efficiencies. Andrielli et al. In 2013 looked at the use of a commercial product ARP system to reduce the costs of soil surveying for precision viticulture. This work was conducted in the Mediterranean viticultural districts. The aim of this research was to produce and minimise the cost of soil sampling via optimising the automatic recessivity profiling methodology. This paper looked at development and the selecting of the best placement of soil sampling sites to employ soil profile description and analysis. The results from this paper indicated that clay could be correlated to apparent electrical recessivity, or ERA for short, and this correlation was good and acceptable. Therefore, the outcomes from this research are that thermomethodology can be used as a measure of soil clay in many Mediterranean viticultural districts. This was concluded as the soils across many Mediterranean viticultural districts are similar. If this technology is used, it is anticipated that cost reductions for both soil sampling and laboratory analysis can be expected. Some work published in Precision Agriculture Journal shows the significance of winemaking and how that might be able to improve quality if you zone your vineyard. This paper looks specifically at how you might use early grape sampling in order to determine the management zones. This article states that precision viticulture can increase profitability by linking vineyard zones to wine quality requirements, thus reflecting in-field variability. In this study, the evaluation of how relevant early grape sampling is to be used as a tool for defining within vineyard zonal areas was assessed. The outcomes of this paper were several. It showed that zone delineation using post-veraison data was provided to be oenologically relevant. It also showed that zone delineation is dependent upon the timing of sample collection, and that ideally data collection after veraison date is required. This study was carried out in 2010 and 2011 on a 4.2 hectare vineyard. They gridded 60 sampling points. 300 berry samplings were collected after veraison and at harvest. Before veraison, information was also used. They used techniques such as fuzzy k-means analysis and subsequent application of zoning procedure to account for membership degree and neighbourhood criteria. These are all elements of the statistics. The timing of precision agricultural technology adoption in the US cotton production was investigated and published in the Precision Agricultural Journal in 2014. The aim of this paper was to look at the timing of technology adoption, which tends to be influenced by profitability and farmers' ability to bear risk. This paper acknowledges there is a range of farmer acceptance to try new technologies, from those innovators who tend to take more risk than the laggards who tend to take less risk. Understanding the factors influencing early adoption of precision agricultural technologies is important for anticipating the technology diffusion over time. In this paper, they use cotton industry as the enterprise of study. However, it may be noted that the outcomes here could be applied to other industries. The factors influencing the timing of grid soil sampling, yield monitoring, and remote sensing all play a part in adoption by cotton producers, and this was evaluated in this research using multivariate censored regression, a statistical technique. As part of the setup of this study, they had to start by hypothesizing factors that might influence adoption timing. These were Influence of the timing of adoption included the farm characteristics, precision agriculture information sources, adoption of other PA technologies, and the location of the farm. It was important to understand these to set out the methodologies correctly. The outcomes of the research into technologies of PA and adoption in the cotton industry was certainly mixed. There was no uniforming hypothesis of either a farm component or another criteria base for adoption. Let's study this in a bit more detail. Land ownership, for example, was associated with the timing of grid soil sampling adoption, a technology used in the cotton industry PA. But land ownership did not impact on the uptake of yield monitoring or remote sensing adoption. Farmer age was correlated with the timing of grid soil sampling and yield monitoring, but not that of remote sensing. It was shown that obtaining precision agriculture information from consultants affected the timing of grid soil sampling and remote sensing adoption, but not that of yield monitoring. Therefore, it may be concluded that there are other factors correlated with early adoption of all of these three technologies. The potential for improved environmental quality appears to be strong adoption motivator across PA technologies, as noted in this research outcome too. And this brings us to our final case study, a global overview of precision agriculture. The outcomes here are based on the Zhang et al. 2002 paper on precision agriculture, a worldwide overview. This was published in the journals Computers and Electronics in Agriculture. The aim of this article was to provide an overview of both the development of PA and the current status of precision agriculture globally. One of the components that it started with was a look at both the spatial and temporal variability. These included adaptations and aspects of yield variability, field variability, soil variability, crop variability, variability in anomalous factors, and management variability. These 6 key components drive the need for both spatial and temporal variability in PA. Zhang et al. Also concluded in their review that managing the variability can be achieved by 2 approaches. There is the map-based approach and the sensor-based approach. They set out arguments, advantages and disadvantages for both of these technologies. Management zones based on site-specific applications of agricultural inputs can be implemented by dividing a field into smaller management zones that are more homogeneous in properties of interest than the field as a whole. In this paper, they state that the impact of PA can be seen predominantly across 2 areas: profitability for the producers and ecological and environment benefits to the public. PA has seemed to be tracking and optimizing of farm production. This tends to be based on the ability for spatial and temporal requirements that can then be matched to variability requirements of your fertilizer and/or your agrochemical applications. It has been noted in this paper that economic impacts can be difficult to measure. Where whole farm PA is undertaken, benefits for improving profit potential and reducing risk can be observed. Precision agriculture research started in the US, Canada, Australia and Western Europe in between the mid to late 1980s, while adoption has been very limited in all of these countries. The limitation of adoption has been reviewed in this paper. Where adoption has occurred, it has been suggested that it is limited to the fitting of existing field machineries by adding both controllers and GPS units. The largest application of PA has been that of applying fertilisers. In Australia, monitoring and mapping spatial variability has been seen in small grain crops yields, and it has received much publicity. The crop yield monitors exist for potatoes, peanut and forage harvesters and are regularly used in Australia. In Australia, under development is the cotton harvesters to monitor both quantitative and qualitative parameters. It has been suggested the total number of grain yield monitors operating in Australia is below 200 at present. That was in 2002. While comparing the USA, and at this time, there was between 5,000 and 10,000 operating units. In Japan, there has been recently investment via the Ministry of Agriculture. This is focusing on sensing and controls related to agricultural mechanisms. Japanese agriculture suffers from great diversity in field size, crop variability, field elevation, water management schemes, climate and soil. It is believed that PA technologies can fit into different farm scales only after reorganisation of the agricultural structure occurs. Using the paper as a resource, it can be found on Moodle. Compare the uptake of precision agriculture in the US with that of Australia precision agriculture. Please insert your notes here. After completing this lecture and reading the associated materials, you should have a solid knowledge of precision agriculture. You should be able to describe all of its components and list its technologies and understand how its technology gives you an output. You should be able to relate this knowledge across a number of examples, that is, across a number of industries. You should be able to state how each industry's productivity or economic outcomes are improved with the installation of PA. You should also understand and be able to give examples of some of the many barriers to adoption, many of which we have discussed here and have been presented in the various papers for you to cite in Moodle. This brings us to the end of Lecture 15 on precision agriculture.